Everyone knew what Einstein believed. God does not play dice with the universe. He had written those words in 1926 in a letter to his friend Max Born, and for 14 years he had refused to change his mind. The greatest physicist alive believed that the universe, at its deepest level, could not be random. There had to be hidden rules, hidden order, something beneath the chaos. And in the winter of 1940, I was about to stand in front of him and present an idea that would challenge everything he held sacred. I was 22 years old. I had no idea what I was getting into. You have to understand what Einstein was fighting against. In 1926, quantum mechanics had taken over physics. Heisenberg, Bohr, and Schrödinger had built a new theory that explained the behavior of atoms and electrons with extraordinary precision. But this theory came with a price. It said that nature, at its most fundamental level, was random. You could not predict exactly where an electron would be. You could not know exactly when a radioactive atom would decay. You could only calculate probabilities, chances, odds. This drove Einstein insane. Not because he didn't understand the math. Einstein understood the math better than almost anyone. He had helped create quantum theory. His 1905 paper on the photoelectric effect was one of the founding documents of the field. No, Einstein's objection was deeper than mathematics. It was philosophical. It was almost religious. Quantum mechanics is certainly imposing, he wrote to Born, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. The old one. That was Einstein's word for God, not a personal God who answers prayers. Einstein didn't believe in that, but a cosmic order, a deep harmony, a universe that made sense. And to Einstein, a universe built on chance did not make sense. I am convinced that he does not throw dice. For 14 years, Einstein had argued with Bohr at conferences. He had proposed thought experiments designed to expose flaws in quantum mechanics. Each time, Bohr had found a way to defend the theory, but Einstein never gave up. That was the man I was about to face. I had come to Princeton in 1939 as a graduate student. My advisor was John Wheeler, a young professor, only 7 years older than me, but already brilliant. Wheeler was different from most physicists. He didn't just want to solve problems within the existing framework. He wanted to rebuild physics from the ground up, and he saw something in me. He said my name, Feynman, and asked, "What if everything we know about electromagnetic fields is wrong?" That got my attention. The standard picture of physics went like this. Charged particles create electromagnetic fields, and those fields carry forces from one particle to another. It's a beautiful idea. It explains light, radio waves, the force between magnets, almost everything. But there was a problem. When you tried to apply quantum mechanics to this picture, you got infinities. The equations blew up. The energy of an electron interacting with its own field came out as infinite, which was obviously nonsense. Wheeler had a radical idea. What if we could eliminate the field entirely? What if, instead of fields, particles interacted directly with each other, across space and time? I know how that sounds. It sounds crazy. But when I worked through the mathematics, something remarkable happened. The infinities disappeared. There was a catch, though. To make the math work, we had to allow something strange. Signals traveling backward in time. Not information. Not messages you could use to change the past. But a kind of echo. A response from the future that perfectly balanced the equations. Wheeler loved it. I loved it. We called it the Wheeler-Feynman absorber theory, but we both knew what it really was. It was an attack on the foundations of physics, an attack on fields, an attack on the way everyone, including Einstein, thought the universe worked, and Wheeler wanted me to present it to everyone, including Einstein. The seminar room at Princeton was small, maybe 30 seats. I arrived early and started writing equations on the blackboard, trying to calm my nerves. It did not work. Eugene Wigner came in first. He had organized the seminar. Then John von Neumann, the mathematician who could multiply 8-digit numbers in his head. Then Wolfgang Pauli walked in. Pauli was famous for two things: his exclusion principle, which explained why matter has structure, and his tongue, which was sharper than a razor. He had once told a physicist that his theory was not even wrong, meaning it was so confused it could not even be tested. And then Einstein walked in. He came straight up to me. I was standing at the blackboard, chalk in my hand, heart pounding. He said hello in his soft German accent. He said he was coming to my seminar, but first he should warn me. He said he had never been able to believe that quantum mechanics was the final word. He smiled. I did not know what to say, so I just nodded. The presentation began. I explained the problem, the infinities, the self-interaction, the conceptual mess at the heart of electrodynamics. I explained our solution, particles interacting directly, across space and time, without fields. As I spoke, I watched Einstein's face. He was following every step. His eyes were focused, his brow slightly furrowed. He wasn't hostile, he was thinking. When I finished, there was a moment of silence. Then Pauli spoke. Pauli said, I do not think this theory can be right. He listed his objections: technical, precise, devastating. Then he turned to Professor Einstein and asked, Don't you agree, Professor Einstein? This was the moment. Pauli, the great critic, was asking the great Einstein to confirm his criticism, to demolish my theory together. Einstein paused. The room was silent. Then he spoke. Einstein said a long, drawn-out, very German, no. Einstein said that he found only that it would be very difficult to make a corresponding theory for gravitational interaction. He meant it would be hard to apply our approach to general relativity, his own theory. Then he said something I will never forget. Einstein said, but after all, general relativity is not so well established as electrodynamics. I would not use that as an argument against you. Do you understand what happened? Albert Einstein, the man who invented general relativity, who had spent his life defending determinism against quantum randomness, had just admitted that even his own masterpiece might not be the final word. He wasn't agreeing with me. He wasn't saying I was right about physics, but he was saying something more important. He was saying, keep pushing. If you're enjoying this story, subscribe. I tell the human stories behind the greatest discoveries in physics. Years passed. The Wheeler-Feynman absorber theory never became the standard approach. Pauli may have been right about some of his objections, but something from that work stayed with me. The idea was that you could think about physics differently. Instead of asking what field exists at a point in space, you could ask what paths a particle takes through space and time. In 1948, I published a paper that changed how we think about quantum mechanics. It was called the path integral formulation. The basic idea was this: a particle does not take one path from A to B. It takes all possible paths. Every path you can imagine, straight, curved, zigzag, or backward, contributes to the final answer. You add them all up, weighted by their action, and the result is the probability of finding the particle at B all paths. All possibilities, summed together. Here is what is strange. This approach gives exactly the same answers as standard quantum mechanics. It is not a different theory. It is a different way of seeing the same theory. But it changed how I understood Einstein's objection. Einstein said God does not play dice. He meant that the universe should not be random. There should be rules, order, cause, and effect. And in a way, my path integral says he was right. The universe is not random. It is the opposite. It is everything at once. Every path happens. Every possibility is real. The randomness we observe is not chaos. It is the result of all these paths interfering with each other, like waves in a pond. Does that mean Einstein would have accepted quantum mechanics if he had lived to see my approach? I don't know. Probably not. He was stubborn. Brilliantly, magnificently stubborn. But I think he would have appreciated the attempt, because that is what he taught me in that seminar room at Princeton. Not a formula, not a technique. He taught me that the greatest scientists aren't the ones who defend their ideas to the death. They are the ones who stay curious. They keep asking questions. They say perhaps instead of impossible. Einstein walked into that room believing that God doesn't play dice. He walked out still believing it. But he had listened to a 22-year-old nobody who thought differently, and he had told me to keep going. Einstein died in 1955, still searching for a unified theory that would explain away the randomness of quantum mechanics. He never found it. I won the Nobel Prize in 1965, partly for work that grew out of those ideas I first presented at Princeton. Did I prove Einstein wrong? I don't think that's the right question. The right question is, did we push physics forward? And the answer is, yes. Both of us. Together. A giant who refused to believe in dice, and a kid from Far Rockaway who was not afraid to disagree. That's how science works. Not by proving people wrong, by taking their questions seriously. I was Richard Feynman, and Einstein made me a better physicist by believing I might be wrong. If this story resonated with you, subscribe and join me for the next one.